Good evening, everyone. So today I'm discussing you about a principle of moment. So what is actually principle of moment? Okay. So let us consider this is a principle of moment. Before doing this, see, this is a rod. Okay, or we can say it as a lever. Let it be lever, and it is pivoted at a point O. So pivot means what? There is a point at which it is being kept. Okay, and there is a force F1 downward direction, and there is a force F2. Both the force are kept in such a way that body is in equilibrium. Body is neither rotating but neither one side moving. Body is in equilibrium. Equilibrium. Okay. Now, if for equilibrium condition total force must be equal to 0, so can we write here, since F1 is in downward direction, so minus F1, and reaction force as we have kept here, so there will be definitely a reaction force, so reaction force is equal to plus R, and this is minus F2, and this is equal to 0. So can we write here R is equal to F1 plus F2? Now for rotational equilibrium, total moment about this point, so since about this point should be 0 because in a body is in equilibrium, so try to find the moment about this point. So we know that moment or torque we need to find, so torque or moment is equal to force into perpendicular distance. So since this is your force and this is a perpendicular distance, that is d1, so F1 into d1, so take it anti-clockwise is positive. Now F2 into d2, F2 into d2 as clockwise direction is negative, so this must be equal to 0. So by using this we are getting F1 d1 is equal to F2 d2. I hope you have understood now, right? Now since F1 is equal to F2 d2, so can we write here F1 by F2 is equal to d2 by d1? Now tell me, mechanical, what do you mean by mechanical advantage? Mechanical advantage is equal to load divided by effort, right? So since if an object is put here, this is your load, okay, this is your load suppose, and you are applying a force or effort to lift this, load. See here, you want to lift the load, with the help of lever, lever, and this is your what, pivot point. Now tell me, if you are lifting by an effort, so effort is your F2, okay. Now mechanical advantage is equal to F1 by F2, and that is equal to d2 by d1. So if you want that our effort should be less effort is required to lift the load, it means that mechanical advantage should be greater than 1. Why so? Because load is greater and effort is smaller, then mechanical advantage is greater than 1. And if mechanical advantage is greater than means, it means that you need to apply less effort, definitely. So if you want less effort, so what you do? So to make a mechanical advantage greater than 1, you have to use increase d2. d2 must be greater than d1. The more you increase d2, that is this effort arm, this is known as effort arm. So if you increase effort arm, then, and this is your load arm, and you decrease load arm, so load arm should be less and effort arm should be more. So in this situation you will able to lift the object very heavy load easily. So this is the basic fundamental thing, that effort arm should be greater than load arm. I hope you have understood now. Now we have to enter moment of inertia, next important topic, that is moment of inertia. What is moment of inertia? It is a property of a body due to which it opposes any change in the state of a rest or a uniform motion. So let us consider then object. When you apply a force, so what happened? It resists. and this property we have called inertia. But in case of a rotation, what happens? Moment of inertia is the moment of inertia. We require moment of inertia. Okay. So moment of inertia plays an important role, similar to the mass plays an important role in linear motion. For linear motion, more mass is there. It means that more force we have to apply to change its position or change its state. Similarly, here moment of inertia is more. It means that more torque is required. The moment of inertia of a particle with respect to an axis of a rotation is equal to the product of the mass of the particle and the square of the distance between the rotational axis. See, suppose this is a mass or a particle and this is the r distance r. Okay. So if I want inertia, so inertia can we write here I is equal to m r square, where m is the mass of the particle and r is the distance from the axis of a rotation, distance from the axis of the rotation. So I is equal to mr square, I is equal to mr square. Understood? So I hope you have understood now. Now moment of inertia of a system of particle. So if particles, so many particles are there, R1, R2 and R3, then moment of inertia I is equal to M1 R1 square, M2 R2 square plus dot 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 Mn Rn square. So here we are getting so many particles. So total, if you want, see here, suppose this is your system and system has many particles, 1, 2, 3, like this. It may happens there is a load like this, there is a mass like this, there is a mass attached like this, there is mass attached like this. Everyone has a r1, this it has r2, it has r3, it has r4. This is the mass m1, this is mass m2, this is mass m3, this is mass m4, likewise. So if you want total inertia of the system, then how you will do? Just you do m1 r1 square, m2 r2 square plus dot 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 mn rn square. So no matter how many particles are there. So for discrete particle, we can use the moment inertia we need to find. Then you can find like this, summation of m into r square. Now for continuous distribution, for example, there is a lumps mass. Lumps mass means everywhere mass is continuously distributed. So moment of inertia can be written as, see here, radius square will be remain same. So small mass can be added by integrating this. So this is the best formula. Now what is the SI unit? So SI unit is your kg per kg meter square. SI unit is your kg meter square. Okay. So I hope you have understood this, right? Now what are the factors affecting the moment of inertia? I, how can I be changed? If mass of body will change, I will change. If mass distribution patterns are changed, for example, here we have considered more mass, here we have considered less mass. It means that it will affect the inertia. Inertia will shift toward this. Okay. Size and shape. Size is very important, shape is very important. It is not like that only mass is required. This shape has a different moment of inertia, this shape has a different moment of inertia. In spite of same mass also, two different shapes has a different moment of inertia. Now axis of rotation. See here, if axis of rotation is here, moment of inertia is different. If axis of rotation is at this point, moment of inertia will be different. If axis of rotation is here, so moment of inertia will be different. So these are the four factors where you can easily tell that factor, this type of factors affects the moment of inertia of any body. Okay. So hope you have understood this. Now I will talk about kinetic energy for a rotational motion. So what is kinetic energy for a rotational motion? Let us consider. So see, this is the this is any of the object lumped mass, and it has so many particles, m1, m2, r1, r2, so many particles are there. But I will take only one particle having r as a distance and mass as m1 or m. Now having a mass m and radius r, and it has initial velocity v. Suppose it is rotating it at omega, so its initial linear velocity will be v, yes or no, if it is being rotated as v omega. So can we write here kinetic energy at that instant as half into mv square, because as we know that kinetic energy is a formula, a half mv square if it is in linear. So for that instant, now we need to convert this in a rotational form. So now then we know that equation of rotation, that V is equal to R omega. So can we put here V is equal to R omega whole square? So what you will get, half m R square into omega square. Okay. So half mr square. Now tell me what is mr square. So mr square is your I and omega square is omega. So finally kinetic energy for a rotational motion is half I omega square. So this thing you should remember. Kinetic energy in case of rotation is equal to half. In place of mass you change inertia into omega square, that is angular velocity. So this is very important. So I hope you have understood now how to convert the kinetic energy of rotational motion from linear one. Okay. Now kinematics of rotation. So this go in a just don't go for details because in your syllabus it is only fews are there. So kinematics of a rotational motion. So these three equation, V is equal to U plus AT, you know, or V naught plus AT, we can initial velocity. X is equal to x naught plus v naught into t plus 1 by 2 at square, you know. X naught is your initial displacement position, u v naught, this is your initial velocity into time t. Okay. And v square is equal to u v naught square plus 2ax. So this is the linear, in context of the linear equation, this is a linear equation. Now you need to change this context. So final velocity can be right here omega, initial velocity can be right here omega naught, can be right omega naught plus at can be right here alpha t, can be right here alpha t. Okay. Now we have got this equation. Now in place of x we can write here theta, initial position theta naught, theta naught means starting position, plus ut means what, initial velocity. So initial angular moment, angular velocity is omega naught into t plus 1 by 2 into angular acceleration is your alpha. In place of linear acceleration we are putting angular acceleration is to time square. Now we have also know that v square is equal to u square plus 2ax. So v square means what, if you replace velocity with the angular velocity, so can we write here omega square. Now in omega v square, u square will be what, omega naught square, because it is your initial angular velocity, plus 2 into alpha, alpha is your acceleration, into change in theta, and that is displacement is your theta minus theta naught. Theta minus theta naught is actually the net displacement. Okay. So in this way we can use this equation in various forms, various problem solving skills. So if you go through the channel, I have already done so many numericals. So I will also do so many exemplar questions of NCERT. So if you want more and more videos to make like this video, so you should support my channel, and as well as you should come and you can also comment in our comment section so that I can solve many numerical problems. Okay. Now see here, conservation of angular momentum, we have already proved that. Okay. Now angular momentum L is equal to I into omega. Okay. So angular momentum is already conserved if no external force is happening. Okay. Now see here, she is sitting on a chair, and uh, her angular velocity is omega and omega. Okay. So linear momentum will be conserved. So linear momentum is constant because if I am not applying external force on this body. So if, now tell me, if I will be changed, so I is equal to mr square. So if girls make hand open the hand, so what will happen, r will change, and if r will change then inertia will change. So if she opens the hand, so angular velocity will also change. Okay. So what happens when girls stage, then what happens, I increase. If I will increase, then L is your constant. See here, L is equal to I into omega, but L is constant. But if she stays the hand, then what happens, I will increase. If I will increase, then to make this linear momentum constant, omega, that is omega, will decrease. And if omega will decrease, it means that angular velocity will decrease. Now if you see close the arm, if she close the arm, so I will decrease. So if I will decrease, then omega will is increase. So if she wants to increase the angular velocity of her body without any external torque or any force or external agent, just she can just move hand, stretch hand. If she will stretch hand, then what will happen, its velocity or angular velocity will decrease. And if she bring back closer arm, then what will happen, her speed will increase. So this is what about conservation of example of conservation of example. It is an example of conservation of linear angular momentum. Okay, so I hope you have understood now. So thank you for watching my video.